Hello there, and welcome back to Bedtime Science. I am really glad you are here tonight. Imagine that a small spacecraft has left Earth with no intention of returning. It passes the Moon, then the orbit of Mars, then Jupiter and Saturn. It crosses the region of icy bodies beyond Neptune and continues into the darkness between the stars. Years become centuries. The sun fades into an ordinary point of light. The Milky Way stretches around the spacecraft as a pale river of stars, and then, after an impossible span of travel, even the galaxy is left behind. Suppose the spacecraft could move faster than any real object is allowed to move. Suppose it could cross millions of light years as easily as a ship crosses an ocean. It passes other galaxies, galaxy clusters, long filaments of matter, and enormous voids where almost nothing shines. What would happen if it continued forever in one direction? Would there eventually be a last galaxy? Would there be a final region of empty space, followed by a wall? Could the spacecraft reach a place where distance no longer continues, where one side contains the universe and the other contains nothing at all? Or would space continue without end? There is a third possibility, stranger than either of those. The universe could contain a finite amount of space and still have no edge. The spacecraft might travel forward without ever meeting a boundary and, after an unimaginably long journey, return from the opposite direction to the place where it began. Modern cosmology cannot yet tell us which of these possibilities describes the whole universe. It can tell us something more subtle. There is an edge to what we can observe, but that edge is not known to be an edge of space. It is a horizon created by the finite age of the universe, the finite speed of light, and the changing geometry through which the light has traveled. Beyond that horizon, the universe almost certainly continues. How far it continues, whether it closes back upon itself, and whether the word beyond has any meaning outside the universe as a whole remain open questions. Tonight, we will follow those questions slowly. We will begin beneath an ancient sky that looked like a roof. We will watch the stars move outward from the small sphere imagined by early astronomers. We will enter the dark night that troubled Johannes Kepler and later became known through the paradox associated with Heinrich Olbers. We will stand beside Albert Einstein as he tries to build a universe that never changes, then follow Alexander Friedman and Georges Lemaitre into a cosmos that expands. We will listen to light that has traveled since the universe was young. We will see how astronomers use that light to test whether space is flat, curved, finite, or wrapped around itself. We will distinguish the horizon we can see today from the more distant boundary that may determine which events can ever reach us in the future. And eventually, we will return to the quiet question that began the journey. So where, if anywhere, could the universe end? For most of human history, the visible sky seemed to offer an obvious answer. The world below appeared solid and limited. The sky above appeared curved. Stars moved across it in repeating patterns, keeping their positions relative to one another while planets wandered among them. It was natural to imagine the stars attached to a distant sphere. In many ancient cosmologies, Earth occupied a central region surrounded by nested celestial shells. The moon belonged to one sphere, the sun to another, the planets to others, and the fixed stars to the outermost sphere. The cosmos was large by ordinary human standards, but it was not endless. An edge did not necessarily mean a wall that a traveler could touch. It could mean the outermost celestial order, beyond which there was no ordinary place. Aristotle argued that the universe was finite and spherical. For him, there could be no physical place outside the outermost sphere because place was defined in relation to containing bodies. Asking what lay beyond the cosmos was therefore not like asking what lay beyond a city wall. It was a misuse of the idea of location. This ancient distinction remains unexpectedly relevant. Even now, When cosmologists say that the universe may not be expanding into anything, they are not saying that a giant object is inflating inside a larger empty chamber. They are saying that the distances within space change. General relativity does not require an external room into which the universe grows. But ancient astronomy placed Earth near the center, and modern cosmology does not. The first great expansion of the known world came through measurement. Greek astronomers estimated the size of Earth, the distance to the moon, and the relative scale of the sun. Their numbers were not always correct, but the method changed the question. The heavens could be approached geometrically. Much later, the invention of the telescope revealed that the sky was not a smooth set of perfect lights. The moon had mountains and shadows. Jupiter had moons of its own. Venus passed through phases. The Milky Way dissolved into countless faint stars. The celestial roof began to recede. Nicholas Copernicus displaced Earth from the center of planetary motion. Johannes Kepler replaced perfect circles with ellipses. Galileo's observations weakened the idea that the heavens were made from a fundamentally different and perfect substance. Yet even a sun-centered system could still be enclosed by a distant shell of stars. The question of whether the stars continued forever remained. In the 16th century, Giordano Bruno argued for an infinite universe filled with innumerable suns and worlds. His cosmology was bound together with philosophical and theological commitments, and his execution cannot be reduced to one scientific claim. But the image he defended was radical. No final sphere, no central world, no privileged boundary. Infinity had entered the night sky. It also created a problem. If the universe were infinite, eternal, static, and filled more or less uniformly with stars, why would the night sky be dark? Look in almost any direction through a sufficiently large forest. Eventually, the line of sight ends against a tree. If stars filled an infinite universe with roughly constant density, then every line of sight should eventually end on the surface of a star. More distant stars appear smaller and dimmer, but there are more of them in larger shells of space. In a simple calculation, the decreasing brightness of each star is balanced by the increasing number of stars. The entire sky should glow with something like the brightness of a stellar surface. But night is dark. Kepler used the darkness of the sky as an argument against an infinite uniform field of stars. Edmund Halley and others examined related questions. In the 19th century, Heinrich Wilhelm Olbers gave a famous account of the problem, and his name became attached to it, although he was not the first to recognize it. Olbers suggested that interstellar material might block the light, but an eternal absorbing cloud would eventually heat until it radiated as much energy as it received. Dust cannot permanently hide an infinite eternal sky. The Real resolution required ideas that were not yet available. The universe has a finite age in its current expanding form. Light from sufficiently distant regions has not had time to arrive. Stars did not exist forever. The universe expands, stretching and weakening radiation. Stellar populations form, evolve, and die. The darkness of night is therefore a cosmological observation. Every dark space between the stars tells us that the visible universe is not an eternal, static, uniformly shining infinity. The night does not prove that all space is finite. It reveals that cosmic history matters. Isaac Newton imagined space differently from Aristotle. Newtonian space was vast, absolute, and independent of the objects within it. It could extend without limit even where there was no matter. Time flowed uniformly everywhere. Matter moved through this fixed stage under the influence of gravity. Newton recognized a difficulty in placing a finite collection of stars inside infinite space. Gravity would pull them together. He suggested that an infinite and approximately uniform distribution might avoid choosing one central point toward which everything collapsed. But the balance would be unstable. Small irregularities could grow. A static universe filled with gravitating matter is difficult to preserve. This problem returned when Einstein completed general relativity in 1915. In Newton's theory, gravity acts within space. In general relativity, matter and energy shape space-time itself. Geometry is no longer a passive background. The distribution of matter helps determine how distances and time behave. Einstein initially believed that the universe as a whole should be static. When he applied his equations to a cosmos filled with matter, however, the equations did not naturally remain still. Gravity encouraged contraction. To hold the universe in balance, Einstein introduced a new term into the equations, the cosmological constant. It acted, in the static model, as a large-scale repulsive effect opposing the attraction of matter. The resulting universe was finite but had no boundary. To understand this possibility, begin with a two-dimensional surface. The surface of Earth has a finite area. A traveler can move north, south, east, or west without encountering an edge. There is no place on the surface where the ground simply ends. Travel far enough along a great circle and the traveler returns to the starting point. The surface is finite and unbounded. Einstein's static universe used a three-dimensional version of this geometry. Space curved back upon itself, not as a sphere sitting inside a larger visible space, but through its own internal geometry. The analogy with Earth's surface is helpful and dangerous at the same time. A two-dimensional sphere is easy to picture because we can view it from a third dimension. A curved, three-dimensional space does not need to curve into an ordinary fourth spatial direction that we could travel through. Curvature can be defined internally by measurements made within the space. Creatures living only on a sphere could discover curvature without leaving the surface. They could draw large triangles and measure their angles. On a positively curved sphere, the angles of a sufficiently large triangle add to more than 180 degrees. Lines that begin parallel may eventually meet. In a negatively curved geometry, like a saddle, the angles add to less than 180 degrees, and initially parallel paths diverge. In flat Euclidean geometry, the familiar rules hold. Einstein's static cosmos was elegant, but unstable. A slight expansion would upset the balance and continue expanding. A slight contraction would continue contracting. And nature was already preparing a different answer. In 1922, the Russian mathematician and meteorologist Alexander Friedmann published solutions to Einstein's equations in which the universe changed with time. Space could expand from a denser state, contract, or follow other histories depending on its contents and curvature. Einstein initially objected, believing there was an error. He later withdrew the criticism. Friedmann had taken the equations seriously even when they contradicted the preferred picture of a static cosmos. A few years later, Georges Lemaitre independently developed an expanding model and connected it with astronomical observations. Lemaitre was a Belgian physicist, mathematician, and priest. He understood that the redshifts of distant galaxies could reflect the expansion of space. He derived a relationship between distance and recession that would later become famous. The light from a distant galaxy contains patterns produced by atoms. When those patterns are shifted toward longer, redder wavelengths, astronomers call the effect a redshift. Motion through space can produce redshift. But in cosmology, the changing scale of space itself stretches the wavelength during the light's journey. Lemaitre combined available distances and velocities and estimated an expansion rate. His work received less attention than it deserved, partly because the relevant paper appeared in French and an important numerical section was omitted from a later English translation. The history of cosmic expansion is therefore not the story of one sudden discovery by one person. The scale of the universe had to be built from several discoveries that were made by people who were not always given equal space in the final story. At Harvard College Observatory, Henrietta Swan Leavitt studied photographic plates containing thousands of stars in the Magellanic Clouds. The plates recorded brightness as tiny black marks. Leavitt compared variables that brightened and faded, carefully sorting patterns that other observers might have regarded as repetitive clerical work. She noticed that a certain class of pulsating stars followed a rule. The longer the period between peaks of brightness, the greater the star's true luminosity. The stars were Cepheid variables. Because the Cepheids in each Magellanic Cloud were all approximately the same distance from Earth, differences in their apparent brightness mostly reflected differences in true brightness. Once the relation was calibrated, a Cepheid's pulsation period could reveal how bright it really was. Compare that intrinsic brightness with how faint it appeared, and distance could be estimated. Leavitt had provided astronomy with a ruler long enough to cross interstellar and eventually intergalactic space. At the time, even the dimensions of the Milky Way were uncertain. The pale spiral nebulae seen through telescopes might be small clouds within our own galaxy, or they might be immense systems far beyond it. In 1920, Harlow Shapley and Heber Curtis met in Washington for an event later remembered as the Great Debate. The name suggests a decisive contest with one winner, but history was less tidy. Shapley argued for a very large Milky Way and placed the Sun far from its center, an important correction to older pictures. He considered spiral nebulae to be part of the galactic system. Curtis favored a smaller Milky Way and argued that the spirals were independent island universes. Each man was right about some things and wrong about others. The debate could not be settled by rhetoric alone because the required distances were not yet secure. That changed when Edwin Hubble examined photographic plates taken with the 100-inch Hooker telescope at Mount Wilson. In 1923, he identified a variable star in the Andromeda Nebula. On an earlier plate, he had marked the object as a possible nova, then crossed out the N and wrote VAR when its changing brightness revealed a Cepheid. The star's period gave a distance far beyond the accepted size of the Milky Way. Andromeda was not a nearby cloud. It was another galaxy. The universe had expanded without any galaxy moving that night. The expansion occurred in human knowledge. A system once thought to contain everything became one galaxy among many. Distance measurements were still imperfect, and Hubble's early numerical scale was substantially wrong. Cepheids come in different populations, calibration improved, and the cosmic distance ladder was revised repeatedly. But the qualitative discovery survived every correction. The Milky Way had no claim to be the entire stellar universe. Besto-Slipher's redshifts now had a new meaning because the spiral nebulae were known to be distant galaxies. Milton Humason, who had begun at Mount Wilson in practical jobs before becoming an observer, obtained spectra from faint systems that required long, patient exposures. Lemaitre recognized the expanding solution in the equations and connected it with the developing observations. The famous relation between recession and distance was assembled through theory, glass plates, variable stars, spectra, and work distributed across many lives. By the end of the 1920s, the pattern was clear enough to transform cosmology. More distant galaxies were generally more strongly redshifted. The universe was not static. If galaxies are moving away in every direction, it is tempting to place our galaxy at the center of an explosion. But that is not what the observation means. Imagine dots painted on a stretching rubber sheet. As the sheet expands, every dot sees other dots moving away. A dot does not need to occupy the center of the sheet. Or imagine raisins distributed through rising bread. As the dough expands, the distance between every pair of raisins increases. From any raisin, the others recede, with more distant raisins generally separating faster. The analogies capture one essential idea. Expansion can occur everywhere without one central point inside the expanding space. They also have limits. Bread expands into an oven, and a rubber sheet has edges in and outside. The universe does not need either. The analogies showed changing internal distances, not the global shape of reality. The Big Bang was therefore not an explosion from one location into surrounding emptiness. In the standard cosmological description, the early universe was hot and dense everywhere within the region that became our observable universe. When cosmologists run the expansion backward, the distances between widely separated locations shrink. Every present location was once much closer to every other present location. There was no single point in today's space where the Big Bang happened. It happened everywhere. This does not mean that the observable universe was always the whole universe. It means that the matter and radiation now visible to us occupied a much smaller region in the past. The equations of general relativity, followed backward under ordinary assumptions, lead toward an initial singularity where density and curvature become infinite. Most physicists do not treat that infinity as a known physical object. It marks the breakdown of the classical theory. A quantum theory of gravity would be required to describe the earliest regime reliably. The phrase age of the universe refers to the time elapsed since the hot early phase described by the Standard Model, approximately 13.8 billion years. This number creates an apparent puzzle. If the universe is about 13.8 billion years old, how can the observable universe have a present radius of roughly 46 billion light-years? Nothing has outrun light through its local region of space. The answer is that the space through which the light traveled expanded while the light was traveling. Imagine a photon beginning its journey toward us billions of years ago. It always moves locally at the speed of light. But the distance between large, widely separated regions changes during the journey. Early in its path, expansion may carry the photon away from us even while it travels toward us locally. Later, as conditions change, it begins making net progress. By the time the photon arrives, the matter that emitted it may be much farther away in present-day distance than the light travel time multiplied by the speed of light. Cosmology therefore uses several different distances. There is look-back time, how long the light has traveled. There is the distance the source had when it emitted the light. There is the present proper distance assigned within a chosen cosmological model. There are luminosity and angular diameter distances connected to how bright and how large an object appears. At ordinary scales, these distances nearly agree. Across the expanding universe, they do not. The observable universe is not simply a sphere with radius 13.8 billion light-years. In the standard cosmological model, matter whose oldest light is reaching us today is now about 46 billion light-years away in comoving distance. That gives the observable universe a present diameter of roughly 93 billion light-years. The number depends slightly on the cosmological parameters used, but the main lesson does not. A universe can be 13.8 billion years old and contain an observable region much wider than 27.6 billion light-years because distance changed during the journey. The boundary of this observable region is called the particle horizon. It is the greatest comoving distance from which a signal could have reached us since the beginning of the hot cosmic history, under the assumed model. The particle horizon is not made of matter. It is not a shell floating around the Milky Way. If a spacecraft somehow approached the location we currently associate with it, the horizon would not be waiting there as a wall. The spacecraft would have its own observable universe centered upon itself. Every observer has a horizon. This is one of the most important ideas in the entire story. The observable universe is centered on Earth only because Earth is the place from which we observe. An astronomer in a galaxy 10 billion light-years away would see a different observable sphere centered on that galaxy. The two spheres would overlap greatly, but each would contain regions unavailable to the other. No observer occupies the center of the whole universe merely by occupying the center of an observable region. A person standing in fog is always at the center of the visible circle. The fog does not make the person the center of the landscape. Cosmic horizons are more fundamental than fog because they arise from space-time and light travel, not from weather. But the distinction between visible region and total region is similar. The oldest electromagnetic light we can observe does not come from the particle horizon itself. It comes from a surface known as the last scattering surface. Early in cosmic history, the universe was filled with hot plasma. Electrons moved freely rather than remaining bound to atomic nuclei. Photons scattered repeatedly from charged particles and could not travel long distances in straight lines. The universe was opaque. As expansion continued, the temperature fell. Roughly 380,000 years after the hot beginning, electrons and nuclei combined into neutral atoms. Photons could travel much more freely. That released radiation now observed as the cosmic microwave background. The light has been stretched by expansion from visible and infrared wavelengths into microwaves. Its temperature today is about 2.7 Kelvin above absolute zero. When a microwave telescope looks in any direction, it sees back toward the era when the universe became transparent. The result is a glowing shell around us, not because we are inside a material sphere, but because looking farther means looking earlier. The cosmic microwave background is not located at one fixed set of galaxies. As time passes, photons from slightly more distant matter reach us. The last scattering surface is defined by events in our past light cone. The sky becomes a map of time. The signal Penzias and Wilson found had a history before it reached their antenna. In the 1940s, George Gamow and his collaborators Ralph Alpher and Robert Herman considered what a hot early universe should have produced. If the universe had once been dense enough for nuclear reactions, the radiation from that era should not simply disappear. Expansion would stretch its wavelengths and cool it, leaving a faint background throughout space. Alpher and Herman estimated that the relic temperature should now be only a few degrees above absolute zero. The prediction attracted limited attention and was partly forgotten as cosmology divided between the hot Big Bang and the steady-state theory. The steady-state universe expanded but maintained the same average appearance through time by continually creating matter. It possessed no dense, hot beginning and therefore no relic thermal glow. The competing pictures did not differ only in philosophy. They predicted different skies. By the early 1960s, Robert Dicke, Jim Peebles, Peter Roll, and David Wilkinson at Princeton had returned to the possibility of ancient background radiation. They began preparing an instrument to search for it. At Bell Telephone Laboratories, Arno Penzias and Robert Wilson were using a horn antenna originally developed for satellite communication. The instrument was designed to receive weak microwave signals with very little interference from its own electronics. An unwanted background persisted. It did not follow the sun, the plane of the Milky Way, or any ordinary direction in the sky. It remained through different seasons. The researchers checked cables, components, atmospheric effects, and radio sources. They cleaned nesting material and droppings left by pigeons from the antenna. The noise remained. A conversation connected Bell Labs with the Princeton group. Two papers appeared side by side in 1965, one reporting the unexplained antenna temperature and another interpreting it as the relic radiation of a hot early universe. The discovery strongly favored the Big Bang picture over the steady state. It also illustrates how evidence often arrives. A theorist may predict a phenomenon, another group may prepare to search for it, and an instrument built for a different purpose may detect it first as a stubborn imperfection. The universe had been speaking through what looked like noise. In 1964, Penzias and Wilson had not set out to confirm the Big Bang. They were trying to understand their instrument. The connection with Princeton transformed the persistent background into cosmological evidence. The discovery did not merely support an expanding cosmos. It gave cosmologists a surface on which the geometry and early conditions of the universe had left measurable patterns. Its temperature varies by tiny amounts, roughly parts in 100,000. Those variations correspond to differences in density and motion in the young universe. Gravity amplified the denser regions over billions of years, helping to form galaxies, clusters, filaments, and voids. Every large structure in the night sky grew from a universe that was almost smooth. The pattern also acts as a standard ruler. Sound waves moved through the early plasma. Gravity pulled matter inward, while radiation pressure pushed outward. These acoustic oscillations created a preferred physical scale. When the universe became transparent, the pattern was frozen into the distribution of matter and radiation. Cosmologists know how large that sound horizon ruler should be within a model. They measure how large it appears on the microwave sky. If space is strongly curved, the apparent angle differs. A positively curved universe alters the path geometry one way. A negatively curved universe alters it another. A flat universe produces the familiar relation between physical size and angle. The observed pattern indicates that the geometry of the observable universe is very close to spatially flat. This does not prove that the whole universe is infinite. It tells us that within the region we can test, curvature is small. Earth looks flat across a garden even though its surface is globally spherical. A much larger cosmos could be gently curved beyond our ability to detect. The flatness itself created a puzzle. In an expanding universe, a small deviation from exact flatness can grow in relative importance when the equations are run through ordinary early cosmic evolution. For the universe to remain as close to flat as observations indicate, the early conditions appear to require extraordinary precision. Another puzzle came from the uniform temperature of the microwave sky. Regions on opposite sides of the sky are very similar. In a simple non-inflationary Big Bang model, many of those regions would not have been close enough to exchange signals and reach the same temperature before the cosmic microwave background formed. How did they become so uniform? Cosmic inflation was proposed as an answer. In 1980 and 1981, physicists including Alexei Starobinsky and Alan Guth developed models in which the very early universe passed through a brief phase of accelerated expansion. Guth recognized that such expansion could dilute unwanted relic particles and drive the geometry toward flatness. The idea evolved quickly. André Linde, Andreas Albrecht, Paul Steinhardt, and others developed versions that allowed inflation to end more successfully and produce a hot universe. Inflation does not mean that matter flew faster than light through nearby space. It means that the scale of space grew extremely rapidly. General relativity allows sufficiently distant locations to separate faster than light because the speed limit applies to local motion and signals, not to the growth of the metric distance between faraway moving regions. During inflation, a tiny causally connected patch could be stretched until it became far larger than the observable universe. Regions now seen in opposite directions could once have shared conditions before being driven apart. Any initial spatial curvature would be stretched toward near flatness, much as a small patch of an enormous sphere appears flat. Inflation also offered an origin for structure. Quantum fields cannot remain perfectly uniform. They contain fluctuations. During rapid expansion, fluctuations on microscopic scales can be stretched to astronomical size. Later, they become variations in density. Gravity turns those variations into the cosmic web. In this picture, galaxies began as amplified quantum irregularities. The evidence for inflation is indirect but substantial. The universe is close to flat. The primordial fluctuations are nearly scale invariant, close to Gaussian, and mostly adiabatic, in broad agreement with simple inflationary expectations. But inflation is not one fully confirmed mechanism. There are many models with different fields and potentials. The particle or field responsible has not been identified. The exact energy scale is unknown. The duration is not measured directly. Popular statements that the entire observable universe grew from a precise size, such as smaller than a proton to a grapefruit in an exact fraction of a second, depend strongly on the chosen model and can give a false sense of certainty. The honest statement is quieter. A period of very early accelerated expansion explains several observations elegantly, and current data are compatible with many inflationary models. But the underlying physics remains unknown. One hoped for clue is a background of primordial gravitational waves. Quantum fluctuations in space-time during inflation could leave a twisting pattern called B-mode polarization in the cosmic microwave background. Experiments have searched for it with increasing sensitivity. In 2014, the BICEP2 team announced a possible detection. The signal later proved to be strongly affected by polarized dust in the Milky Way. No convincing primordial B-mode detection has yet established inflationary gravitational waves. The search continues because the signal could reveal the energy scale and eliminate broad families of models. Meanwhile, the microwave sky places limits on the shape of space. Geometry answers one question: how does space behave locally and across large scales? Topology answers another: how is space connected globally? A flat universe can be infinite, extending endlessly in every direction. But flat space can also be finite if opposite regions connect. Imagine an old video game in which a character leaving the right edge of the screen reappears on the left. Leaving the top may return the character from the bottom. The screen is displayed as a rectangle, but the character experiences no boundary. Opposite sides are identified. A two-dimensional version can be represented as a torus, though the familiar donut shape bends in three-dimensional space and does not preserve perfect flatness on its surface. Mathematically, the internal geometry can remain flat when opposite edges are joined. Three-dimensional space could behave similarly. Travel far enough in one direction and return from the opposite direction. Space would have a finite volume, but no edge. Light could circle the universe, allowing multiple images of the same galaxy or the same region of the microwave background. Other topologies are possible in flat, positively curved, and negatively curved geometries. The global shape may be far more complicated than a simple sphere or torus. How could astronomers test a topology larger than any possible journey? They look for repetition. If space wraps around on a scale smaller than the observable universe, the same distant object might be visible in several directions. But identifying repeated galaxies is difficult because each image would show the object at a different age and angle. The cosmic microwave background offers a cleaner test. If the last scattering surface intersects itself through the topology, matching circles could appear in different regions of the sky. The temperature pattern along one circle would correspond to another. Searches in Planck and earlier data have not found convincing matched circles or other evidence that the observable universe wraps around on a detectable scale. This does not prove that space is infinite or topologically simple. It means that if space is finite through certain tested topologies, the repeating scale must be large enough that the expected pattern is absent from the region we can observe. A room can be too large for a person inside it to discover that opposite walls connect. The observable universe may occupy only a small portion of the whole geometry. This is why flatness does not answer the original question. Space may be infinite and unbounded. It may be finite and unbounded. Current observations do not support an ordinary boundary where space stops. No established cosmological model requires a wall at the outer edge. The word edge appears because horizons look like boundaries on diagrams. But a horizon is a boundary of information, not necessarily a boundary of existence. To understand the difference, we need to follow light more carefully. At any event in space-time, light defines a cone of possible influence. The past light cone contains events that could have sent a signal arriving here now. The future light cone contains events that a signal emitted here now could eventually influence. Events outside both regions are separated in such a way that no ordinary signal can connect them at this moment without exceeding the local speed of light. The observable universe is the intersection of our location with a long cosmic past. Every galaxy we see is seen at an earlier time. The Andromeda Galaxy appears as it was about 2.5 million years ago. A galaxy 1 billion light-years away is seen roughly a billion years into its past, with cosmological corrections depending on distance. The microwave background is seen when the universe was only a small fraction of its current age. Looking outward is looking backward. There is no single photograph of what the entire universe is doing now. The word now becomes difficult across cosmic distances because relativity provides no universal simultaneity independent of coordinates and motion. Cosmologists define a useful cosmic time for observers moving with the average expansion, but this is part of a highly symmetric model rather than a signal that can be received instantaneously from everywhere. When a diagram shows a sphere 46 billion light-years in radius, it is not showing what a giant camera could photograph from outside. It is reconstructing a present distance slice through a model using light that arrived from many different ages. The observable universe is therefore a history arranged as a sphere. The particle horizon grows in one sense as time passes. Light from regions previously too distant has more time to arrive. But expansion complicates the story. Some regions we see today are already so distant that signals they emit now may never reach us. Their ancient light arrives, yet their future becomes permanently hidden. This introduces another boundary, the cosmological event horizon. The particle horizon asks which events have been able to influence us by now. The event horizon asks which events will ever be able to influence us, even if we wait forever. These are not the same surface. In a universe where expansion eventually slows sufficiently, light from more and more distant regions might continue arriving without a permanent event horizon. In a universe whose accelerated expansion persists, there are regions from which signals sent now can never overcome the increasing separation. We can observe a galaxy in its youth while being unable ever to receive the message it sends today. The distinction is almost poetic. The past remains visible after the future connection has been lost. Another often confused scale is the Hubble radius. The Hubble law relates recession rate to distance. At a certain distance, the model's recession rate equals the speed of light. This scale is called the Hubble radius. It is not generally a solid horizon. Galaxies beyond the Hubble radius can be observed. Their light may have been carried away from us at first by expansion and later entered a region where it could make progress. The Hubble radius changes over cosmic time. Saying that a galaxy recedes faster than light does not violate relativity. Special relativity forbids an object from passing a nearby observer through local space faster than light. Cosmological recession is the increase of distance between widely separated comoving locations due to the geometry's evolution. No galaxy locally overtakes a beam of light beside it. The total distance between us and that galaxy can still grow faster than light could cross a static space. This is why the phrase edge of the observable universe must be handled carefully. The most distant matter we can in principle receive ancient signals from is not separated by one simple speed boundary. The answer depends on the entire history of expansion. Cosmology is the study of paths through changing geometry. That geometry is shaped by the contents of the universe. Ordinary matter attracts. Radiation contributes. Dark matter gravitates. Dark energy, in the simplest model, drives accelerated expansion. For much of the 20th century, astronomers expected cosmic expansion to slow. Every galaxy and every cloud of matter pulled gravitationally on the others. Unless the universe expanded fast enough to escape forever, perhaps it would eventually stop and collapse. Researchers wanted to measure the deceleration. Type 1a supernovae offered a way. A Type 1a supernova occurs when a white dwarf undergoes a thermonuclear explosion under particular circumstances. The details of progenitor systems are varied and remain an active subject, so the old image of every event reaching one identical critical mass is too simple. But the light curves can be standardized well enough to estimate their intrinsic brightness. Compare intrinsic brightness with apparent brightness, and distance can be inferred. In the 1990s, two teams searched for distant Type 1a supernovae. They expected the objects to show how strongly the universe had slowed. Instead, the supernovae were dimmer and therefore farther away than a decelerating model predicted. The expansion had accelerated. The announcement in 1998 transformed cosmology. Saul Perlmutter, Brian Schmidt, and Adam Rees later shared the Nobel Prize for the discovery. A term Einstein had introduced to hold the universe still returned in a completely different role. The cosmological constant could represent a uniform energy density of empty space. Unlike matter, its density does not dilute as space expands. As the universe grows, matter becomes more spread out while the vacuum contribution remains. Eventually, the vacuum-like component dominates the large-scale dynamics and acceleration begins. The name dark energy covers this unknown cause of acceleration. In the standard lambda cold dark matter model, dark energy is a cosmological constant, represented by the Greek letter lambda. It accounts for roughly 2/3 of the present cosmic energy budget. Dark matter contributes roughly another quarter, and ordinary baryonic matter only a small remainder. These percentages are model-dependent summaries of gravitational behavior, not a direct inventory of substances stored in separate containers. Dark energy is especially mysterious because the simplest quantum estimates of vacuum energy do not naturally match the small observed value. The discrepancy is one of the deepest problems in theoretical physics. The cosmological constant also creates an event horizon if acceleration continues. Distant galaxies not gravitationally bound to our local group will cross beyond future communication. Their light will become increasingly redshifted and faint. After an enormous time, observers in our merged local galaxy may see little evidence of the wider cosmos. The visible universe of the future may become much smaller in practice, even while the underlying space grows. A horizon does not stay fixed like a fence. Objects cross it in the sense that future signals cease to arrive. Nothing locally dramatic happens to the galaxy at that moment. Its own observers see ordinary surroundings and place themselves at the center of their own horizon. Horizons are observer-dependent structures in space-time. This is familiar from black holes. A black hole event horizon is a boundary beyond which signals cannot escape to the outside universe. It is not necessarily a material membrane. A large black hole's horizon can be crossed without a local flash or wall. A cosmological event horizon is different in origin, but it shares the idea of a causal boundary. What lies beyond may be real while remaining unable to send us information. Physics is filled with regions that exist in equations but cannot be contacted from a given world line. The evidence for accelerated expansion is supported by several independent observations. Within the standard cosmological model, that behavior is represented by dark energy, but its physical nature is not known. Supernovae trace distance. Baryon acoustic oscillations provide a standard ruler in the distribution of galaxies. The cosmic microwave background constrains early conditions. Weak gravitational lensing traces the growth and distribution of matter. Galaxy clusters, redshift space distortions, and other probes add information. Together, these measurements fit the lambda cold dark matter model remarkably well. Yet precision has revealed tensions. One is the Hubble tension. The Hubble constant describes the current expansion rate. Measurements based on the early universe, especially the cosmic microwave background interpreted through the Standard Model, produce a value near the high 60s in kilometers per second per megaparsec. Measurements built from the local distance ladder, including Cepheid variable stars and Type 1a supernovae, often produce a value in the low 70s. The difference is small in ordinary language and significant in precision cosmology. James Webb Space Telescope observations have strengthened confidence that simple crowding errors in Hubble's Cepheid measurements are not enough to erase the discrepancy. Other local methods and alternative calibrations produce a more complicated landscape, and researchers continue investigating systematics. The Hubble tension may indicate an overlooked measurement problem. It may indicate missing physics in the early universe or later expansion. It has not been solved. A second tension concerns dark energy itself. The Dark Energy Spectroscopic Instrument, known as DESI, measures the spectra and positions of millions of galaxies and quasars to map cosmic expansion through baryon acoustic oscillations. Results released from 3 years of observations in 2025 strengthen hints that dark energy might evolve with time when DESI data were combined with the cosmic microwave background and particular supernova samples. The statistical preference depended on which supernova compilation was included and on the assumed parameterization. That dependence matters. A hint is not a discovery. The DESI baryon acoustic oscillation measurements themselves remain broadly well described by the Standard Model. The suggestion of evolving dark energy emerges from combinations of datasets that are extraordinarily precise and not perfectly consistent. The careful conclusion remains that a changing dark energy component is an intriguing possibility, not an established fact. DESI has completed its planned 5-year mapping observations, while analysis of the full survey continues. Euclid is building another immense map through galaxy clustering and weak gravitational lensing. The Vera C. Rubin Observatory began its 10-year legacy survey of space and time in 2026, adding repeated imaging, supernovae, and vast samples of changing objects. NASA's Roman Space Telescope is designed to measure cosmic expansion and structure with complementary methods. The fate of the universe is therefore not settled by one number. If dark energy remains a constant, accelerated expansion continues indefinitely. If it changes, horizons and long-term evolution may change with it. A component whose pressure becomes sufficiently negative could produce a future in which acceleration grows until structures are disrupted, a speculative scenario called the Big Rip. If the effective dark energy weakens or changes sign, expansion could evolve very differently, perhaps even allowing recollapse under some models. Current evidence does not justify choosing these dramatic outcomes over the simpler cosmological constant. The quiet truth is that the largest scale future depends on the least understood dominant component of the present universe. Dark energy shapes which regions can remain causally connected. Dark matter shapes where galaxies form. Dark matter does not emit, absorb, or scatter ordinary light in any readily detected way, but its gravity reveals it. Stars orbit within galaxies faster than visible matter alone can explain. Galaxy clusters bend background light more strongly than their luminous contents allow. The early formation of structure requires additional gravitating matter that does not interact with photons like ordinary plasma. The cosmic microwave background records its influence. The cosmic web grows around its gravitational scaffolding. Whatever dark matter is, it appears to be mostly non-baryonic and cold enough in the Standard Model to form structure efficiently. Decades of searches for proposed particles have not yet identified it. Weakly interacting massive particles remain possible across reduced parameter regions. Axions and axion-like particles are active candidates. Sterile neutrinos, ultralight fields, primordial black holes within constrained mass ranges, and more exotic possibilities continue to be studied. Modified gravity theories attempt to reproduce some observations without the standard dark matter interpretation, but matching the full range of cosmological and cluster evidence is difficult. The unknown contents of the universe therefore affect the answer to its shape. Curvature depends on total energy density and dynamics. But the old rule that density alone determines whether the universe expands forever or recollapses is no longer sufficient once dark energy is included. A positively curved universe can expand forever. A flat universe can have different futures depending on its components. Geometry, topology, and destiny must be separated. Cosmology learned these distinctions slowly because ordinary intuition tries to compress them into one picture. A closed universe sounds like a sealed box. An open universe sounds like a room with an exit. But closed and open in older cosmological language refer mainly to curvature and possible expansion histories, not to walls and doors. A closed positively curved space can have no edge. An open negatively curved space can still be complete and boundaryless. A flat space can be infinite or compact. Words borrowed from everyday containers become misleading at cosmic scale. The same problem appears when asking what the universe expands into. A balloon analogy shows galaxies separating on a surface, but the balloon expands into the surrounding room. People then imagine the universe expanding into a higher dimensional emptiness. Some mathematical models can embed curved spaces inside higher dimensional ones, and certain speculative physical theories include extra dimensions. But ordinary cosmological expansion does not require such an exterior. The intrinsic distance between points changes. Imagine a ruler drawn on a flexible mathematical grid. The grid scale changes everywhere. No external direction is needed in the equations describing the grid's internal geometry. Asking what lies outside all space may resemble asking what lies 1 meter north of the North Pole on Earth's surface. The phrase assumes a continuation that the geometry does not provide. This does not prove that no larger reality exists. A universe like ours could, in some speculative models, be a region within a larger inflating space-time, a brane in a higher dimensional structure, or one branch of a quantum state. The point is narrower. The standard expanding universe model does not need an outside, and observation has not revealed one. The universe in physics usually means all space-time and physical contents under discussion. If something can interact with our universe, many physicists would simply include it in a larger definition of the universe. The edge moves with the definition. The observable universe has a horizon. The whole universe may have global topology. A proposed multiverse may contain many domains. Language must identify which level is meant before the question can be answered. The simplest region beyond our horizon is not necessarily exotic at all. If space continues much farther than we can see, there should be more galaxies, matter, radiation, and cosmic web beyond the particle horizon, governed by approximately the same laws and emerging from similar early conditions. This is sometimes called a level 1 multiverse, though calling it a multiverse can make an ordinary continuation of space sound more dramatic than it is. We cannot directly observe those regions today. But the remarkable uniformity and large-scale homogeneity within our observable domain make a reasonably smooth continuation plausible. The cosmological principle assumes that, when averaged over sufficiently large scales, the universe is statistically homogeneous and isotropic. Homogeneous means no location is fundamentally special in its large-scale properties. Isotropic means no direction is fundamentally special. The microwave background is highly isotropic after accounting for our motion and foregrounds. Galaxy surveys approach homogeneity on large scales despite immense structure on smaller ones. The cosmological principle is an empirical approximation, not a statement that every region contains the same galaxy. A forest can be statistically uniform across a landscape while containing clearings, streams, and dense groves. Our observable universe contains voids, filaments, walls, clusters, and superclusters. These structures do not violate homogeneity when averaged across sufficiently large volumes. Their distribution forms the cosmic web. Computer simulations begin with tiny density variations inferred from the microwave background. Dark matter falls into slightly denser regions. Filaments grow. Gas flows into halos. Galaxies form where cooling, feedback, star formation, black holes, and mergers interact. The result resembles survey maps of the real universe. Some matter lies in dense knots containing galaxy clusters. More lies along filaments and sheets. Enormous voids occupy much of the volume. A void is not absolute nothingness. It contains dark matter, thin gas, radiation, and scattered galaxies, but at lower density than the cosmic average. Cosmic structures acquire striking names, and claims about the very largest structures require caution. Apparent walls or groupings spanning billions of light years can depend on how objects are selected, how significance is calculated, and whether the pattern exceeds what a random realization of the standard model can produce. Not every named giant structure is a single gravitationally connected object. The cosmic web itself is well established. The status of particular record-breaking structures can be much less certain. This matters because an alleged structure too large for homogeneity is often presented as a crisis before the statistical question is resolved. The universe is large enough to generate unusual-looking patterns. A map containing billions of objects will contain coincidences. Cosmology must distinguish a genuine new scale from the human tendency to connect points. Baryon acoustic oscillations provide a more reliable large-scale feature. The early plasma's sound waves left a slight preference for galaxies to be separated by a particular comoving scale, roughly 150 megaparsecs. The effect is not a rigid shell around every galaxy. It is a small statistical excess in the probability of finding another galaxy at that separation. Because the scale can be calibrated from early universe physics, it serves as a cosmic ruler. Measure the ruler across the sky and along the line of sight at different redshifts, and the expansion history can be reconstructed. This is how a pattern in the infant universe becomes a tool for measuring dark energy billions of years later. The cosmic web also teaches why no last galaxy can define an edge. Even if a traveler reached a region with no visible galaxies nearby, emptiness would not imply that space had ended. Voids are real parts of the universe. A final luminous object would not necessarily be a final location. The universe could contain regions beyond star formation, beyond matter density, or beyond our horizon without terminating geometry. An edge is a property of space, not of where the lights happen to stop. Our spacecraft could leave the last galaxy in a finite island of matter and continue through empty space if the geometry allowed it. Conversely, a finite wrapped universe could contain galaxies everywhere and still return the spacecraft to its starting point. Matter distribution and spatial topology are separate. The question now becomes more difficult. Can the universe be proven infinite? No observation can survey an actual infinity. Measurements can show that the universe extends at least as far as the observable region and that curvature is small. They can place lower limits on the size of particular finite models. But a universe larger than the horizon can imitate infinity perfectly within everything we see. Suppose space were positively curved with a curvature radius 1,000 times larger than the observable universe. Every triangle we could draw would appear nearly Euclidean. No circumnavigating light would have returned. No repeated pattern would be visible. Such a universe could be finite beyond all practical detection. Infinity is a mathematical conclusion drawn from a model, not an object seen through a telescope. The same caution applies to finiteness. No current observation has detected the global closure of space. The scientifically responsible answer remains conditional. If the simplest exactly flat, topologically trivial model extends globally, space is infinite. If space has compact topology or sufficiently small positive curvature, it may be finite and unbounded. The data do not reveal a physical edge. What lies beyond the observable horizon cannot be photographed, but not every statement about it is equally speculative. A continuation of the same large-scale universe is the conservative possibility. Eternal inflation is a more ambitious one. In many inflationary models, the field driving accelerated expansion does not end inflation everywhere at once. Quantum fluctuations cause different regions to evolve differently. In some patches, inflation ends and energy is converted into particles and radiation. In others, inflation continues. Because the inflating regions expand so rapidly, the process may never end globally even while it ends locally again and again. Each region where inflation ends can become a vast hot Big Bang domain. Our observable universe would be contained within one such domain. The popular image is a foam of bubble universes forming within an eternally inflating background. The word bubble is metaphorical. These domains are regions of space-time governed by fields and geometry, not soap spheres floating through ordinary air. Different bubbles might settle into different vacuum states. If a deeper theory permits several possible low-energy arrangements, particle masses, forces, or effective constants could differ from one region to another. This creates the inflationary multiverse. The idea is not an optional fantasy added merely for drama. Eternal behavior arises naturally in broad classes of inflationary models. But natural within a model is not the same as observationally established. Other bubbles may be permanently separated from us by continued inflation. Signals cannot cross the intervening geometry. The theory then faces a serious question. What observations can distinguish it from alternatives? One possibility is that our domain collided with another bubble in the early universe, leaving a pattern in the cosmic microwave background. Searches have not produced compelling evidence for such a collision. Another route is indirect. If a well-tested fundamental theory predicts a landscape of vacuum states and an inflationary mechanism known independently, the multiverse could inherit support from that theory. No such complete chain has yet been confirmed. Eternal inflation also creates a problem of probabilities. If every possible event occurs infinitely many times in an endlessly inflating spacetime, how should relative likelihoods be calculated? One must regulate the infinities by choosing a measure, a method of counting regions or observers. Different measures can produce different predictions. This is not a small technical inconvenience. It affects whether the theory explains anything. A framework in which every outcome happens somewhere needs a principled reason why observers should expect one outcome more than another. Without such a rule, the multiverse can become too flexible. The anthropic principle enters here. In its modest form, it states that observations are conditioned by the requirements for observers. We should not be surprised to find ourselves in a region where stars, chemistry, and stable structures are possible, because regions without such conditions contain no observers asking the question. This reasoning can create selection effects. Imagine fish measuring the environments in which fish exist. They will always find liquid water, not because every place contains water, but because fish cannot make measurements in deserts. Applied to cosmology, anthropic selection has been used to discuss the small observed cosmological constant. A much larger positive value could accelerate expansion so early that matter never forms galaxies. A sufficiently large negative value could cause rapid collapse. Observers naturally appear only within a narrower range. The argument can show why observed values need not be typical across a larger ensemble. It does not by itself prove that the ensemble exists, nor does it explain the probability distribution of values within it. The strong forms of anthropic reasoning, claiming that the universe must produce observers or that consciousness determines cosmic properties, go far beyond the modest selection effect. The careful use is limited. Any observation is made from a place compatible with the observer's existence. This is true and occasionally powerful. It is not a complete theory of why the laws are what they are. The multiverse word is also used for several unrelated ideas. Regions beyond our horizon in one continuous space are sometimes called a multiverse. Inflationary domains with different vacuum states are called a multiverse. The many-worlds interpretation of quantum mechanics describes branches of a universal wave function. Some mathematical philosophers propose that every consistent mathematical structure exists physically. These ideas should not be stacked together as though evidence for one supports all the others. A continuous region beyond our particle horizon follows rather directly if the universe is much larger than what we see. Eternal inflation depends on the correct model of the early universe. Quantum branching depends on an interpretation of quantum mechanics. Mathematical multiverses are highly speculative metaphysics. They share a name and differ in scientific status. None provides a known physical edge for our spacecraft. If eternal inflation is correct, the spacecraft cannot simply fly from our region into another bubble like crossing a national border. The causal geometry and continuing expansion may prevent any route. The boundary would not be a wall in ordinary space. It would be a feature of space-time evolution. The phrase other universe can therefore mean something that has no spatial direction from here. Not every separate domain lies somewhere that a compass could point. This returns us to the beginning of time. If the expansion is run backward, distances shrink and temperature rises. The cosmic microwave background gives way to an earlier plasma. Nuclei dissociate into protons and neutrons. At still higher energies, protons and neutrons dissolve into quarks and gluons. Electroweak physics changes form. Beyond experimentally tested energies, uncertainty grows. At about 1 second, the broad outline is well supported. At tiny fractions of a second, particle theory and cosmology guide extrapolation. Near the Planck era, roughly 10 to the minus 43 seconds in a simple timeline, quantum effects of gravity should become essential. Our present theories no longer provide a trustworthy classical spacetime. Asking what happened before the Big Bang assumes that time continues through this boundary. Classical general relativity alone often does not. The singularity theorems developed by Roger Penrose, Stephen Hawking, and others showed that under broad conditions, expanding cosmological spacetimes are geodesically incomplete toward the past. The result does not necessarily say that a physical point of infinite density exists. It says that classical paths cannot be extended indefinitely within the theory. The map ends. Whether reality ends is another question. A singularity can signal that the framework has been pushed beyond its domain. The center of a black hole and the earliest cosmos both confront general relativity with regimes where quantum physics should matter. Physicists have proposed several ways the beginning might be replaced. The Hartle-Hawking no-boundary proposal describes the quantum state of the universe using a geometry in which the distinction between time and space changes near the origin. In simplified language, The beginning resembles the smooth south pole of a sphere rather than a sharp edge. There is no location south of the South Pole on Earth's surface, yet the surface does not break there. Likewise, the proposal attempts to remove a past boundary without placing an earlier ordinary time before it. The analogy is evocative, but the full mathematical construction is difficult, and competing versions of the quantum wave function give different predictions. Loop quantum cosmology applies techniques inspired by loop quantum gravity to highly symmetric models. Quantum geometry can replace the classical singularity with a bounce. A contracting universe precedes the expanding one. The bounce is a result within particular reduced models, not an observed event. String-inspired cosmologies include pre-Big Bang phases, brane collisions, and emergent scenarios. Cyclic models imagine repeated expansions and contractions or successive cosmic eras connected by transformations. In conformal cyclic cosmology, associated with Roger Penrose, the remote future of one cosmic aeon is mathematically related to the beginning of another. Ekpyrotic and cyclic models use slowly contracting phases to smooth the universe before a bounce or collision. Each proposal addresses some puzzles and faces others. A contraction must avoid destructive instabilities. A bounce must be physically controlled. Predictions must distinguish the model from inflation and survive observational tests. No pre-Big Bang history has been confirmed. The phrase "before the Big Bang" may eventually become meaningful within a successful theory. It may also resemble asking what happened before time had the structure required for before. The honest answer is not that we know there was nothing. Nothing is not a measured state outside space-time. The honest answer is that the tested cosmic history reaches back toward a regime where our theories lose authority. The boundary belongs to knowledge before it belongs to the universe. This distinction is essential whenever diagrams show a cone beginning at one point. A cosmological diagram compresses dimensions and represents a model. The narrow early region does not necessarily mean the universe was a tiny ball located in external emptiness. If space is infinite today and the standard homogeneous description is extended backward, it can remain spatially infinite at every time while distances between points become smaller and density becomes higher. Infinity multiplied by a changing scale remains infinite. The observable region occupied a tiny volume, but the whole spatial slice need not have been finite. If space is finite today, it may have been finite and much smaller then. The Big Bang model describes density and expansion, not by itself the total size. This is another reason the phrase "the universe began as a point" is misleading. Our observable universe traces back to a tiny region. The global universe may not. Cosmologists often choose coordinates that expand with the average matter distribution. Galaxies at rest in this comoving grid keep approximately fixed coordinate positions, while the scale factor changes the physical distance between them. The scale factor is assigned a convenient value of 1 today. In the past, it was smaller. In the future, it may grow without bound. This does not mean galaxies themselves swell with the universe. Local forces resist expansion. Atoms are bound electromagnetically. Solar systems and galaxies are gravitationally bound. The space within and around bound systems is described by local geometry, not by simply applying the average cosmic scale factor to every object. A coin does not grow because the universe expands. The distance between unbound galaxy groups does. The boundary between local and cosmological behavior is not a hard shell. It emerges from which forces and geometries dominate. Our local group is gravitationally bound. The Milky Way and Andromeda are moving toward one another despite cosmic expansion, but their final encounter is no longer considered certain. Updated simulations that include measurement uncertainties and the influence of neighboring galaxies allow outcomes ranging from a distant passage to a merger, with some analyses finding roughly even odds of a merger within the next 10 billion years. More distant groups recede with the Hubble flow. In the far future of a cosmological constant universe, the descendants of the local group remain together while almost every galaxy not gravitationally bound to them disappears beyond the event horizon. The universe does not tear local space apart under an ordinary cosmological constant. It isolates islands of bound matter. Imagine astronomers born 100 billion years from now. Their galaxy contains long-lived stars and remnants of many mergers. But the wider cosmic web has faded from view. The cosmic microwave background has been stretched to wavelengths so long and temperatures so low that detection becomes extraordinarily difficult. The evidence for expansion may be hidden. Those astronomers might conclude that their galaxy is surrounded by empty, static space. They would live inside a universe whose history had become observationally inaccessible. We are fortunate to exist during an era when ancient radiation, distant galaxies, expansion, and star formation are all measurable. Cosmic knowledge has a window. The fact that evidence can disappear does not mean the regions cease to exist at the moment they cross our horizon. Their later signals fail to arrive. From their perspective, we are the ones fading away. Every sufficiently separated observer loses access to the others. Accelerated expansion turns one connected visible cosmos into many isolated causal regions. The event horizon is therefore more like a future edge of conversation than an edge of space. Beyond it, events cannot send replies. The surface itself depends on the observer and the future expansion history. If dark energy changes, the horizon can change. An event horizon is defined using the entire infinite future, which means its exact existence cannot be established from one local moment without assumptions about what comes next. This is a strange feature of causal boundaries. To know whether a light signal emitted today will ever reach us, one must know how the universe expands forever. The horizon is a global fact about spacetime. Current data support accelerated expansion, making a future horizon likely under the simplest model. But cosmology continues measuring the future indirectly through the past. The ultimate long-term story in that model is sometimes called heat death. The name does not mean the universe reaches one ordinary temperature quickly or that all activity stops at one date. It describes a gradual approach toward states with fewer usable energy differences. Stars convert nuclear fuel into radiation. Star formation eventually declines as gas is consumed, expelled, or locked away. Stellar remnants remain. Gravitational encounters rearrange systems. Black holes grow and, over vastly longer times, may evaporate through Hawking radiation if the semi-classical prediction is correct. The timescales become enormous. The era of ordinary stars lasts far longer than the current age of the universe. Degenerate remnants may persist for periods expressed with dozens or more zeros. Proton decay, if it occurs, depends on physics not yet observed. Black hole evaporation for the largest holes takes incomprehensibly longer. Dark energy determines the expanding background throughout this slow transformation. A universe can continue forever while becoming increasingly empty and cold. There is still no spatial edge. There is a temporal direction toward dilution and equilibrium. If the universe instead recollapsed, the scale factor could reach a maximum and shrink. Distant galaxies would approach, radiation would blue shift, and density would rise. A big crunch once seemed connected simply to positive curvature. Dark energy separated those ideas. Current accelerated expansion makes near-term recollapse inconsistent with the simplest interpretation of observations. It remains possible only in models where the dark energy behavior changes significantly. A big rip requires an even more unusual component, often called phantom energy, with an effective equation of state below a particular threshold. In such models, acceleration strengthens until clusters, galaxies, planetary systems, molecules, and eventually space-time structures are disrupted. Current data do not establish phantom energy. The dramatic scenario is useful for showing that the future depends on the equation of state, but it should not be presented as the expected fate. The ordinary cosmological constant leads to isolation and heat death, not the tearing of atoms by expansion. Cosmology offers many endings because the dominant unknown is measured through subtle effects across billions of light years. The edge question contains a similar uncertainty. An infinite universe and a vast finite universe can look identical from inside one horizon. Could a future technology settle the issue? Better measurements of curvature can increase the minimum size of a finite curved universe. More precise microwave maps can search for topological patterns. Galaxy surveys can look for repeated structures, though cosmic evolution complicates them. 21-centimeter radiation from neutral hydrogen may eventually map enormous volumes and early epochs beyond current galaxy surveys. Primordial gravitational waves or other relics could reveal the physics of inflation and indirectly favor certain global models. But a fundamental limit remains. Information outside our causal past has not arrived. No telescope can collect a photon that space-time has not allowed to reach it. Technology can approach physical limits. It cannot negotiate with causality. If the global topology leaves no signature inside our horizon and curvature is too small to measure, the universe's total size may remain undecidable from observation. Science can know that a question has several compatible answers. That is not failure. It is knowledge about the boundary of knowledge. The observable horizon is not a permanent set of named galaxies. As time passes, new ancient regions can enter our particle horizon, while accelerated expansion removes future contact with many regions. We receive the earliest chapters from places whose later chapters we will never read. The cosmic book opens backward and closes forward. A photon arriving tonight may have begun its path before Earth existed. During its journey, galaxies formed, stars enriched matter, planets assembled, life emerged, and human beings built a detector. The emitting galaxy may now lie beyond our future reach. The photon is a message from a relationship that no longer permits conversation. This gives the observable universe an edge in time more than in space. At the farthest electromagnetic view, we meet the opaque early plasma. Beyond it in look-back time, neutrinos and gravitational waves could in principle carry information from earlier epochs because they interacted differently, though detecting a primordial neutrino background or inflationary gravitational waves is extraordinarily challenging. The microwave background is not the beginning. It is the earliest wall through which ordinary light cannot see. Like the surface of a fog bank, it hides what lies earlier, not what lies farther in a simple spatial sense. The universe has several horizons depending on the messenger. Photons have a last scattering surface. Neutrinos decoupled earlier. Gravitational waves could travel from still earlier events. Each channel provides a different cosmic depth. No messenger currently gives a direct view of the Planck regime. The edge moves when the method changes. This pattern appears throughout science. The naked eye once ended at a dark sky. Telescopes revealed stars. Larger telescopes revealed galaxies. Radio receivers revealed the microwave background. Gravitational wave detectors revealed mergers hidden from ordinary light. Every instrument expands the observable world. But the particle horizon is not merely an engineering limitation. It follows from causal history. Even a perfect telescope has a past light cone. The universe may be larger than every possible observation. Perhaps infinitely larger. Perhaps only several times larger in a direction that wraps around too slowly to reveal itself. perhaps embedded in a global geometry for which ordinary words like size and shape capture only approximations. Quantum gravity may eventually alter the concept of space itself. In some approaches, space-time is not fundamental. It emerges from quantum relations, entanglement, causal networks, or more primitive structures. If space emerges, asking for its edge at the deepest level may be like asking for the edge of temperature inside one molecule. Temperature is real for large collections, but not fundamental for an isolated particle. Space could be real and measurable while arising only in an appropriate large-scale description. Holographic ideas suggest that information within a region of gravity may be encoded in ways related to its boundary area. The ADS/CFT correspondence provides a precise example in certain spacetimes. A gravitational theory in a higher dimensional bulk can correspond to a non-gravitational quantum theory on a lower dimensional boundary. Our observed universe is not the simple anti-de Sitter spacetime where the best understood correspondence applies. The holographic principle does not mean we have discovered a literal screen at the edge of the cosmos. It suggests that geometry and information may be related more deeply than ordinary intuition allows. The word boundary in holography is mathematical and causal, not evidence of a wall outside the galaxies. Other quantum gravity approaches replace smooth space with discrete networks or histories. Loop quantum gravity quantizes geometric quantities in particular formulations. Causal set theory begins with ordered events. Tensor network models explore how geometry might arise from patterns of entanglement. These remain active research programs rather than completed descriptions of our universe. But they share a possibility. The question, where does space end, may eventually be replaced by what relations generate space, and where does that description cease to apply? An emergent universe can be boundaryless at one level and encoded by boundaries at another. Cosmology already taught a smaller version of this lesson. The apparent edge of the sky became a horizon. The apparent center became an observer-dependent viewpoint. The apparent explosion became expanding geometry. The apparent emptiness became fields and dark energy. Questions survive while their meanings change. Let us return to the impossible spacecraft. It has crossed the local group and watched the Milky Way fade. It has passed through the Virgo region, moved beyond nearby superclusters, and traveled along filaments traced by galaxies. The journey cannot occur in reality as imagined. No massive spacecraft can move faster than light locally, and crossing the observable universe at sublight speed would take longer than stars, galaxies, and the cosmic environment remain unchanged. But the thought experiment can separate possible geometries. In the first possibility, space is infinite, flat, and topologically simple. The spacecraft continues forever. It does not travel toward a boundary. It travels toward new locations. If the cosmological principle remains valid, no final direction becomes special. There may be regions with more galaxies, fewer galaxies, different local histories, and rare arrangements, but no ultimate wall. The number of galaxies could be infinite even though the density at any location remains finite. Infinity is not a place at the end. The spacecraft never reaches the moment when all earlier distance has been crossed. This is difficult for the mind because every ordinary journey has a destination or exhaustion point. An infinite road has neither. At every point, more road remains. If the universe is statistically homogeneous and infinite, sufficiently distant regions may contain arrangements similar to ours through chance, depending on the finite number of possible quantum states in a region and the assumptions used. Popular discussions sometimes claim that exact copies of Earth must occur infinitely often. That conclusion is not as simple as it sounds. It depends on whether space is truly infinite, whether the relevant state space is finite, how quantum states are counted, and whether the large-scale laws remain uniform. The conservative claim is only that infinite space never ends. The second possibility is positive curvature with a finite, unbounded spatial volume. Our spacecraft chooses the straightest possible path, called a geodesic. It never turns by local measurement. After a sufficiently long journey, it could return to its starting region from what once seemed the opposite direction. There would have been no edge along the route. The experience resembles circumnavigating Earth, but with one additional spatial dimension. On Earth, a traveler can point upward away from the surface. In a closed three-dimensional universe, there need not be an accessible external direction corresponding to upward. The returning spacecraft might see the Milky Way at different ages during the journey if light had also circled space. The sky could contain multiple images of cosmic structures, if the circumference were far greater than the particle horizon. However, no returning signal would yet have completed the route. Locally, the universe would look flat and infinite. The third possibility is a compact flat topology. The spacecraft crosses a face of the universe without noticing and re-enters through the identified opposite face. There is no seam with bolts or light. The fields and geometry continue smoothly. A toroidal topology can produce different path lengths in different directions. Travel one way and return sooner. Travel along a diagonal and take longer. Other compact flat manifolds can include twists, so an object returning after a circuit may be reflected or rotated relative to its initial orientation in the mathematical identification. The sky in such a universe could contain repeated patterns arranged according to those symmetries. Again, no repetition has been detected on scales accessible to current searches. A fourth broad possibility is negatively curved and infinite space. Geodesics diverge. Large triangles have angle sums below 180 degrees. The volume contained within a given radius grows faster than in Euclidean space. Certain negatively curved spaces can also be compact and finite through complex identifications, showing once more that curvature alone does not decide infinity. Mathematics offers many boundaryless universes. Observation selects among them only through effects inside our causal region. A universe with a literal spatial boundary would require extra physical rules. What happens to a field at the boundary? Does light reflect, vanish, or pass into something else? Does gravity end? How are conservation laws handled? General relativity allows space-times with boundaries under particular mathematical conditions, but the standard homogeneous cosmological solutions do not introduce an ordinary edge surrounding matter. A sharp boundary would likely leave observational signatures, such as anisotropy, unusual gravitational effects, or a preferred direction, unless it lay far beyond the horizon. No such cosmic wall is observed. The universe appears statistically similar in every direction at large scales. There are local asymmetries. The Milky Way has a plane. Nearby galaxies cluster. Our motion creates a dipole in the cosmic microwave background. Foreground dust and radio emission mark directions. After correcting for known local effects, the primordial sky is remarkably isotropic. A nearby edge would break that symmetry. One side would differ from another. The absence of such evidence does not rule out every distant boundary imaginable, because a boundary placed forever beyond observation cannot be tested. But a hypothesis that makes no observable difference carries little scientific weight. The boundary most often imagined comes from drawing the universe as a circle on paper. A map needs an outer line. The line may represent the particle horizon, the last scattering surface, a coordinate limit, or simply the border of the page. Human vision then turns the line into a physical rim. The same error occurs with maps of Earth. A rectangular world map has left and right edges, but a ship crossing the corresponding longitude does not fall off the planet. The edge belongs to the representation. Astronomical maps often place Earth at the center and distance outward. Nearby galaxies surround the center. Older light appears farther away. The cosmic microwave background forms the outer circle. This map is scientifically useful. It displays our past light cone. It does not show the universe from outside. The outer ring is the limit of the chosen data, not a photograph shell around all existence. Other observers draw different maps. If we could compare maps with a galaxy beyond our current horizon, each observer would place themselves at the center and include regions invisible to the other. The overlap would reveal no privileged middle. This is the modern cosmological principle expressed through horizons. No center has been observed in space, but the Big Bang can be described as a special boundary in time. Every comoving observer traces their history backward toward the hot, dense past. In a space-time diagram, world lines converge as the scale factor shrinks. This can look like a center below the present universe. It is not a point one could locate by traveling left or right. It is an early temporal condition shared across space. The distinction between a spatial center and a temporal origin can be compared to the surface of Earth at sunrise. Every location experiences morning as Earth rotates, but morning is not one place on the ground from which daylight explodes outward. The analogy is imperfect, yet it separates location from era. The early universe is an era. Another source of confusion is the phrase total mass of the universe. Scientists can estimate the average density and multiply by the volume of the observable universe to estimate how much matter lies within our horizon. If the whole universe is infinite and roughly homogeneous, its total matter is infinite in the mathematical model. If it is finite, the total depends on its unknown volume. The observable amount is not the total amount. A jar sampled from an ocean can reveal salinity without revealing the ocean's outer shore. Our cosmological sample is enormous and still possibly tiny relative to the whole. This creates cosmic variance. We observe one universe from one location and one past light cone. Certain large-scale fluctuations have only a few independent modes within the observable volume. No improved instrument can provide another independent universe to average over. Measurements at the largest angular scales, therefore, have an irreducible statistical uncertainty. The cosmic microwave background's broadest patterns may look unusual, including low power at certain scales or alignments discussed in the literature. Some anomalies may be statistical accidents, foreground effects, or hints of physics beyond the standard model. Because there is only one sky, their significance is difficult to establish. A finite topology has sometimes been proposed to explain large-scale anomalies. No model has gained compelling evidence. Cosmic variance sets a boundary on certainty even when instruments become perfect. The universe may hide its global form not through secrecy, but through giving us only one realization. Distance itself is model-dependent at cosmic scale. Astronomers directly measure redshift, angle, flux, time delay, and other observables. Converting these into a distance requires assumptions about geometry and expansion. The statement that the particle horizon is roughly 46 billion light-years away is not read from one ruler. It is inferred by fitting a cosmological model to several datasets and integrating the expansion history. The agreement among observations makes the estimate robust within the standard framework. If the framework changes, the exact distance changes. This does not make cosmology arbitrary. Models must simultaneously fit the microwave background, element abundances, galaxy clustering, supernovae, lensing, and many other observations. Freedom decreases as evidence accumulates. But numbers at the cosmic horizon are not measured like the length of a table. They are reconstructed. One of the earliest reconstructions began with the cosmic distance ladder. Trigonometric parallax measures nearby stars by their apparent shift as Earth orbits the Sun. More distant steps use stars whose intrinsic luminosities can be calibrated. Cepheid variables pulse with periods related to luminosity. Type 1a supernovae extend measurements into distant galaxies. Each rung depends on the one below. Errors can propagate. The local expansion rate is therefore checked with alternative methods. The tip of the red giant branch, surface brightness fluctuations, water megamasers, gravitational wave standard sirens, time delays in gravitational lenses, and other techniques. No single method yet has ended the Hubble tension. The disagreement matters for the edge question because expansion history determines horizon distances. A slightly different current rate does not transform a boundaryless universe into a box, but it changes the inferred scale and future causal structure. Dark energy evolution would matter even more. Cosmologists therefore map not only where galaxies are, but when their light was emitted. A three-dimensional survey is partly a time machine. Nearby objects belong to recent cosmic history. Distant objects belong to earlier epochs. The map mixes space and time. DESI uses thousands of robotically positioned fibers to collect spectra from galaxies and quasars. Each spectrum provides a redshift. Millions of redshifts reveal the expansion and clustering pattern across vast volumes. Euclid photographs large regions from space with stable image quality, measuring shapes distorted by weak gravitational lensing and distances through galaxy clustering. Rubin repeatedly scans the southern sky, allowing changes and explosions to be followed over time. Roman will survey wide areas with space-based resolution. No telescope sees the edge of all space. Together, they chart how the visible domain grew. The cosmic web can be imagined as a fossilized wave pattern stretched and amplified. Its filaments do not form a net surrounding an exterior. They continue through the observable volume and likely beyond it. At the horizon, the map ends because the signal ends. A cartographer in the age of ocean exploration might draw sea monsters beyond known coasts. Modern cosmology should resist filling unknown regions with certainty. It uses extrapolation with error bars. The continuation beyond our horizon is supported by the lack of a special feature near the boundary and by inflationary reasoning. But the exact global structure remains blank. Blank does not mean empty. The distinction can be felt in an ordinary room at night. Close the curtains, and the visible world ends at fabric. The city does not end there. The boundary belongs to information reaching the eyes. A cosmic horizon is not fabric, and no faster motion can simply push it aside. Yet it shares the principle that absence from view is not absence from reality. What does nothing mean beyond an edge? In physics, empty space is not philosophical nothing. Vacuum contains quantum fields in their lowest available state. It has structure, correlations, and measurable effects. General relativity assigns geometry even where matter is absent. A region containing no particles can still possess spacetime. If a literal universe edge separated space from nothing, the outside would not be empty space. It would be no spatial relation at all. There would be no distance into it, no direction, and no duration there unless a larger framework restored those concepts. This is why asking what is outside the universe may fail grammatically at the physical level. The word outside is spatial. If all space is included in the universe, outside has no defined location. A mathematician can discuss an abstract embedding space, but that does not automatically become physical. The surface of a sphere can be described without invoking the volume inside it. Its inhabitants need only measure distances and curvature along the surface. Similarly, general relativity describes the intrinsic four-dimensional spacetime geometry. An external observer is not required. Some people imagine standing outside the universe and seeing its shape. No physical observer can occupy a non-spacetime location. Even in multiverse models, The observer would be inside a larger space-time, and the word universe would have shifted to mean one domain rather than all reality. The ultimate outside retreats. This does not make the question foolish. Human intuition was built in a world of containers. Water is inside a glass. A house stands inside a landscape. Earth moves inside the solar system. The solar system lies inside the Milky Way. The Milky Way lies inside the cosmic web. It is natural to continue the nesting. What contains the universe? Physics answers that containment may stop being the right relation. The universe is not known to be an object located within space. It is the space-time structure in which location is defined. The concept is difficult because every mental image places it inside a larger imagined scene. Even the black background behind an illustration is treated unconsciously as more space. Remove the background and the mind supplies another. Infinity and boundarylessness resist visualization. Mathematics carries the thought where imagery fails. A set of coordinates can continue without bound. A manifold can be compact without boundary. Curvature can be intrinsic. Causal horizons can separate communication without separating existence. Equations do not suffer from the need to view the universe from outside. But equations are not the final word. They describe families of possible worlds. Observation decides which family resembles ours. Our observations currently favor a universe that is spatially flat to high precision within the accessible scale, statistically homogeneous and isotropic on large scales, expanding from a hot, dense early phase and accelerating today. They reveal no topological repetition and no edge. They do not establish global infinity. This answer is less dramatic than a wall and more profound. The universe has no observed center and no observed rim. Every observer sees a horizon because every observer receives only a finite history of light. The horizon is real as a causal limit and not real as the end of space. This dual description causes much of the confusion. A rainbow has a real angle and appearance for an observer, but is not a solid arch that can be reached by driving toward it. A horizon at sea is real as the limit of direct sight, but moves as the observer moves. The cosmic particle horizon is not identical to either phenomenon, but it also depends on the observer's spacetime position. Move, wait, or choose another observer, and the set of observable events changes. No spacecraft catches it from behind. As the spacecraft travels, its past light cone changes. New regions become visible ahead, old relationships change behind, and cosmological expansion evolves during the journey. The original horizon defined from Earth was never a destination. Suppose the impossible spacecraft crosses the current moving location of our particle horizon billions of years from now. Earth's definition of the horizon has changed by then. The spacecraft sees its own surrounding history. Nothing marks the crossing. If it transmits a message home, whether the message arrives depends on the event horizon and the path through spacetime. The journey cannot be described by freezing today's universe and moving through the picture. The universe continues while the traveler moves. This is why science fiction maps of the entire cosmos are conceptually difficult. A map can label moving coordinates at one chosen cosmic time, but no signal can verify the whole slice simultaneously. Relativity allows the model, not a God's eye photograph. The absence of a universal present also complicates the phrase the universe now. For the highly homogeneous cosmological model, a natural family of observers can agree on cosmic time measured since the hot early phase. The cosmic microwave background identifies the frame in which its dipole vanishes. Earth moves relative to that frame. This provides a practical cosmic rest standard without restoring Newton's absolute space. Local motions, gravitational fields, and inhomogeneities produce deviations. The large-scale model is astonishingly successful because averaging turns a lumpy universe into a simpler geometry. The real cosmos contains black holes, rotating galaxies, collapsing clusters, and expanding voids. No one exact scale factor describes every local region. The global average still captures the history of the observable universe. When cosmologists ask whether space is finite, they usually ask about spatial slices within such a model. Alternative ways of slicing spacetime can assign different spatial geometries while preserving the same four-dimensional reality. This reminds us that even the size of the universe at one moment depends partly on how moment is defined. Observable quantities remain the anchor. Light paths, redshifts, angles, correlations, and clock readings are physical. A global volume may be less directly defined in a complex spacetime. The standard question is meaningful within the cosmological symmetries supported by observation. Beyond that framework, the universe may not possess one simple size. A quantum universe could be in a superposition of geometries. A highly irregular spacetime may resist division into universal spatial moments. The phrase shape of the universe is useful and approximate. The impossible spacecraft can now return for the final part of the journey. It began with a simple destination in mind, the edge. That destination has dissolved into several different questions. How far can light have traveled to us? Which events can ever communicate with us? Does space curve back upon itself? Is its volume finite or infinite? Does the word outside describe anything physical? Each question has a different answer, and none requires a wall. The spacecraft could cross the present comoving location that Earth assigns to the particle horizon. Nothing would happen there. Earth's horizon would have changed during the journey, and the traveler would carry a different past light cone. The old map would not contain a rim waiting to be reached. If space is infinite and topologically simple, the journey can continue without end. Every completed distance is followed by more distance. Infinity is not a final region. It is the absence of a final region. If space is finite and positively curved, the craft could follow a geodesic and eventually return without ever turning locally. The path would close because of global geometry. If space is flat but compact, the craft might pass smoothly through an identification in space and later approach familiar structures from another direction. There would be no seam, flash, or sign marking the crossing. If space is negatively curved, it might be infinite, or it might possess a more complicated compact topology. Curvature alone does not decide total size. These possibilities differ greatly, yet they share one feature. None contains an ordinary outer wall. A literal spatial edge would require additional physics. Fields would need rules for how they behave there. Light would need to reflect, stop, or cross. Gravity would need a boundary condition. A nearby edge would probably introduce a preferred direction or other effects into the observable cosmos. No such evidence has appeared. The sky is not perfectly uniform on every scale. Galaxies gather in clusters, filaments, and sheets. Voids occupy enormous volumes. The Milky Way creates a bright band. Our motion creates a dipole in the microwave background. But after local structures and motion are accounted for, the universe is remarkably isotropic on very large scales. A nearby rim would be difficult to hide inside that symmetry. A boundary placed permanently beyond every possible observation could always be imagined. But a boundary that produces no measurable consequence cannot yet function as a scientific explanation. The strongest conclusion is therefore not that a physical edge has been disproved in every conceivable model. It is that no physical edge has been detected, and the successful cosmological models do not require one. The observable universe does have a boundary in a different sense. Its particle horizon marks the limit of events whose signals could have reached our location during cosmic history. In the standard model, the matter associated with that present horizon lies roughly 46 billion light-years away in comoving distance. The observable diameter is therefore about 93 billion light-years. This is not the diameter of all existence. It is the diameter of the region that has been able to send us information. The event horizon asks a different question. If accelerated expansion continues, some events occurring now will never be able to communicate with us, even given unlimited future time. The Hubble radius is different again. It marks a distance at which recession in a chosen cosmological description equals the speed of light at that era. It is not generally the boundary of all observable objects. The cosmic microwave background forms another apparent edge. It is the farthest ordinary electromagnetic light because the earlier plasma was opaque. Neutrinos and gravitational waves could, in principle, carry information from earlier times. The beginning of classical spacetime may introduce another boundary in our theories. These edges do not coincide because they are not the same kind of thing. One limits past information. One limits future communication. One limits a particular messenger. One may mark the breakdown of a theory. None has been shown to be the place where space itself stops. This distinction explains why diagrams can mislead. A circular map of the observable universe places Earth at the center and the microwave background around the outside. The outer circle looks like the shell of a cosmic object, but the map is arranged by look-back time. Nearby galaxies are shown as they were relatively recently. More distant galaxies are shown at earlier stages. The final ring records the era when photons began traveling freely. The page has an edge. The universe represented on it may not. A rectangular map of Earth also has edges. A traveler crossing one side does not fall into nothing. The line belongs to the chosen representation. Every distant observer can draw a cosmic map centered upon themselves. Their observable sphere overlaps ours and extends into regions ours does not include. Being at the center of a past light cone does not make anyone the center of all space. There may be no center of all space. The Big Bang does not provide one. It was not a fireball exploding from a location into emptiness. The hot, dense, early condition occurred throughout the space described by the model. Run the expansion backward, and distances between comoving points shrink everywhere. If global space is infinite now, it could also have been spatially infinite while far denser in the past. If global space is finite now, it could have been finite and smaller. The standard Big Bang model tells us how the scale changed. It does not by itself reveal the total volume. This is why the universe was not necessarily born as one tiny ball. The region that became our observable universe was once extraordinarily small. The whole may have extended beyond it even then. Inflation strengthens the expectation that the universe is much larger than our observable patch. A small causal region can be expanded into a domain far wider than the horizon. But the amount of inflation before observable scales emerged is not known. The total region could be vastly larger than what we see. Some models make it endlessly large. Others allow a finite global topology. No telescope can measure a total size if the identifying features lie entirely beyond causal reach. Science can increase the lower limit. It can improve measurements of curvature. It can search microwave maps for repeated circles. It can compare galaxy patterns. It can test inflation through primordial signals. But if a finite universe is much larger than the observable region and leaves no repeated pattern inside it, that global finiteness may remain hidden. The same observations would fit an infinite universe and a sufficiently large finite one. This is not merely a limitation of current technology. It may be a limit established by causality. No detector can receive a signal that has not had time to arrive. A perfect telescope still possesses a past light cone. The whole universe may therefore be larger than every possible observation made from here. That statement sounds abstract, but every cosmological measurement already begins with this limitation. Astronomers never see a distant galaxy as it is at a universal present. They receive old photons. A galaxy 1 billion light-years away appears in its past. A galaxy billions of light-years farther away appears in a younger cosmic era. The microwave background appears from a time when atoms had only recently formed. The visible universe is a record assembled from different ages. It is not one photograph taken from outside. There is no known outside position from which such a photograph could be made. General relativity describes space-time intrinsically. Curvature can be measured through paths, angles, and distances from within. An embedding in a larger visual space can help imagination, but the larger space is not required by the equations. The surface of Earth can be studied by inhabitants who never leave it. They can discover that geodesics meet and large triangles have unusual angle sums. They do not need to see the planet floating against black space to establish its intrinsic curvature. The universe may demand the same humility with one fewer external viewpoint available. A person can photograph Earth. No observer can leave all space-time and turn a camera back toward it. Even proposed multiverses do not provide an ultimate outside in the ordinary sense. If our observable domain belongs to a larger inflating spacetime, that spacetime becomes the wider physical universe under discussion. If it is embedded in some deeper theory, the question moves to the boundary of that theory. The container keeps becoming part of what is contained. Perhaps space is not fundamental at the deepest level. Some approaches to quantum gravity explore geometry emerging from relations, entanglement, causal order, or discrete quantum structures. In such a theory, asking where space ends might eventually become less basic than asking where the relations that create space change. These ideas remain incomplete. They do not alter the established answer tonight. Within the observable cosmos, space is very close to flat on large scales. No repeated global topology has been convincingly detected. No spatial center has been found. No physical rim has been found. The total extent remains unknown. That is already a remarkable answer. Ancient astronomers placed the stars upon an outer sphere. Modern cosmology replaced the sphere with a horizon. The old sphere was imagined as the boundary of the world. The horizon is understood as the boundary of a conversation. Light from inside it has had time to reach us. Light from beyond it has not. If acceleration continues, some galaxies whose ancient light is visible tonight have already become unreachable by signals sent in their present era. We receive their past after losing their future. A photon can arrive from a relationship that no longer permits a reply. The edge of the observable universe is therefore an edge in causal history more than a shore in space. The universe beyond it need not be exotic. It may contain more cosmic web, more voids, more galaxies, and the same average laws. Or the global structure may eventually reveal connections we cannot currently detect. Eternal inflation may place our region inside a larger mosaic of domains. Quantum cosmology may replace the earliest boundary with a bounce or a smooth beginning. Those ideas occupy different levels of confidence. They should remain possibilities rather than decorations presented as facts. The secure answer can be stated without them. The universe has a finite observable region around our world line. The whole universe may be infinite. It may instead be finite and unbounded. We do not currently know which. Neither option requires an edge. The impossible spacecraft can finally be released from its mission. It no longer needs to search for a wall. If it continues into infinite space, no last place arrives. If it circles a finite topology, the destination becomes the beginning. If causal expansion separates it from Earth, the loss of contact occurs without impact. The craft becomes smaller against the cosmic web. The web becomes a pattern. The pattern becomes the faint memory of sound waves in a young plasma. The young plasma becomes a microwave glow around the sky. And the glow becomes a few signals inside an instrument on one small planet. From those signals, The mind listening tonight can infer that the visible horizon is not a wall. There is no need to picture all 93 billion light-years at once. The number can remain a relationship between age, light, and expansion. There is no need to decide whether the whole is infinite. The uncertainty is real and carefully bounded. There is no need to imagine an exterior darkness surrounding the universe. Darkness is already part of the universe wherever little visible light reaches an eye. The room remains local. Gravity holds the body and the planet together. Electromagnetism holds nearby matter at stable distances. Cosmic expansion acts mainly between distant unbound structures and does not pull the room apart. The solar system continues around the Milky Way. The local group follows its changing path. Faraway galaxies continue sending ancient light. Some photons will arrive long after tonight. Others can never arrive. The horizon remains defined by geometry and history without requiring attention. The question can now become quiet. Does the universe have an edge? Our observable region is limited by a horizon. The whole universe has no known physical edge. It may continue forever, or it may close without a boundary. That is the answer the evidence allows. It is clear enough to rest upon and open enough for future science. The spacecraft can fade into distance. The map can close. The oldest light can continue crossing space. And here, within one small part of the universe that has been able to speak to us, the next breath can be the only distance that matters. Air enters. The body receives it. Air leaves. The room stays quiet. Space does not end beyond the darkness. Only attention becomes softer. Sleep well. Good night.